Welcome everyone. In this video, what we're going to do is we're going to look at chemical bonding, and we're going to introduce two of the main types. As you can see, chemical bonds are forces that hold atoms together, and when these atoms are held together, we form compounds. Two main types of compounds are formed either through ionic bonding, which you will see is due to the transfer of electrons. And then we have another one we'll take a look at a little bit later called covalent bonding, which is the sharing of electrons. Let's start with ionic bonding. With ionic bonding, it's usually done when a metal and a non-metal get together. What you're going to learn is that the metals like to lose electrons, whereas the non-metals like to gain electrons. So what happens here is that the metals are going to transfer their electrons over to the non-metals. As a result, when metals lose electrons, they will become positively charged. They'll become ions, and they're going to be referred to as cations. The nonmetals, as a result of receiving the electrons, will become negatively charged, and they'll become anions. So an ionic bond is a metal and a nonmetal getting together. You can see here that when atoms lose or gain electrons, they become charged. They're known as ions. Notice the cations, such as sodium in the example below, would be an example of a metal losing an electron. So it would be positively charged. It would be a cation. Chlorine would be an example of a nonmetal gaining an electron. It would become negatively charged. And negative ions are known as anions. Now, what determines the way they're going to react is most elements obey something called the octet rule. The octet rule has to do with atoms wanting to achieve 8 electrons in their outermost energy level. The outermost energy level is known as the valence shell, and the electrons in that energy level are referred to as valence electrons. You may recall that the noble gases, the reason they don't react is because they already have 8 valence electrons. And having 8 electrons in the outermost energy level makes them stable. And that's one of the reasons why the noble gases do not react. What we're going to see here is what other atoms like to do to become stable, to become like the noble gases. So here we have the ions again. You'll see that some will lose, whereas some will want to gain electrons in order to be stable. But you're also going to see a third option, where some atoms are stable by sharing electrons. These are known as covalent bonds. We'll talk more in the future on them, but I'll say something briefly. A covalent bond is going to be the sharing of an electron or of electrons between a nonmetal with another nonmetal. Sometimes you might see a metalloid and a nonmetal together. Usually it's two nonmetals sharing electrons. Now, you'll notice this is divided into two parts here. Some covalent bonds are nonpolar, and that means that when they are sharing the electrons, there's an equal sharing of electrons between the two atoms involved. But sometimes you might have unequal sharing of electrons because one of the atoms happens to be greedy. Now, in chemistry, we call these greedy elements electronegative elements. And fluorine is the most electronegative element on the periodic table. In fact, they're all near fluorine. The most electronegative elements are fluorine, oxygen, nitrogen, and chlorine. I use the acronym FUNCL to help you remember those electronegative elements. So if you are making a covalent bond involving fluorine, oxygen, nitrogen, or chlorine, it's most likely will be a polar covalent bond, which simply means that there will be unequal sharing of electrons. So here's a couple of examples of covalent bonds. In the first one on the left here, you have hydrogen sharing electrons. You could see the overlap of their orbitals there. The little blue dots are the electrons that are being shared. Same thing's happening here with oxygen. You'll notice that one is a double bond, which is they're sharing 2 pairs of electrons. And then you got water, and you see the sharing taking place here. Now, notice that the sharing takes place with the outer energy level of each atom. The inner energy level, you could see over here with carbon. Notice the inner energy level, and also here with oxygen, those are known as core electrons. They don't really participate in bonding. it is the valence or the outermost electrons that participate in bonding, whether ionic or covalent. And you could see here that there's a sharing here between the carbon and the 4 hydrogen atoms. And again, those electrons are in the outer energy level. Now, something that we'd like to do is there's a notation known as an electron dot structure, also known as a Lewis dot structure, where we use a dot to represent a valence electron, and then the symbol of the element would represent the nucleus and all the core electrons pertaining to that atom. And if you look at a periodic table here, one way, a quick way to figure out valence electrons is to look at the number here in front of the letter. Now notice I'm only circling what we call the main group elements, which are the tall columns. The transition elements over here, they really don't follow the standard rules like the others. If you recall, group 1A, which is group 1, are the alkali metals. They have one valence electron, and you're going to learn that what they like to do is they like to lose that one electron, so they'll become +1. The alkaline earth metals like to lose 2 electrons. They have 2 valence electrons, so they like to lose the 2, so they become +2. In the future, you'll learn that these guys have their own rules, so we'll talk about them in another video. Here in the boron family, really it's from aluminum down. Boron mainly does covalent, but generally if you're in group 3A, you like to lose 3 electrons. If you're in group 4A, where the carbon family is, I usually leave this blank because those 2 top ones, especially carbon and silicon, they don't do ionic at all. In fact, they share electrons and do covalent. Now, when you get to the nitrogen family, they have 5 valence. So they actually want to gain 3. So by gaining 3, they become -3. The chalcogens have 6 valence electrons, which I circled, and they want to gain 2. Now, notice, if you haven't picked up on this, their goal is to achieve an octet. So if you have 5 valence and you gain 3, that gives you 8. If you have 6 valence and you gain 2, that gives you 8. The halogens have 7, so all they want to do is gain 1 to get the 8. And then when you get to the noble gases, I'll put a 0 there. They are already stable, so they do not want to gain any electrons. So if you're wondering, how were these Lewis dot structures done? Very simple. If you look at sodium, in the periodic table, sodium has just 1 valence electron right up here. So when you do a Lewis dot structure, all you do is put the symbol and then you put 1 dot for the 1 valence electron. And honestly, you can put it wherever you want. I usually put it at the top. Now, chlorine is a halogen. And if you look here, chlorine has 7 valence electrons. So I need to put 7 dots. Now, there's a little rule that we use. And I kind of call it the 4 corners rule. And when you put the 4, well, we got to put 7. This is the way you should do them. You should put 1 in each corner. So here would be 1. Then you put 1 here. Then you put 1 here. That's 3. That's 4. Now, we still got 3 more to add. So when you pair them off, you go 5, 6, and 7. Now, I usually go clockwise. You could go counterclockwise if you want. For instance, you could have simply done 1, 2, 3, 4, 5, 6, 7, and that's fine. As long as you have 3 paired and 1 unpaired, that is correct. So with carbon, you can see that carbon has 4 valence electrons. So you need to do 4 dots. So you put the symbol for carbon and then you go 1, 2, 3, 4. What you don't want to do is this mistake, that you pair them 1, 2, 3, 4. That would be wrong. You want to first put 1 in each, I call it each corner. And then after you fill 1 in each corner, then you pair them off. Let's do another example. Let's say I had oxygen. So the symbol for oxygen is O. If you look at oxygen, it has 6 valence electrons, which means 6 dots. So we're going to go 1, 2, 3, 4, 5, 6. Now, you'll always get this correct, but had somebody done this, that's correct too. As long as you have 2 paired and 2 unpaired, both structures are actually correct. Okay? What you don't want to see would have been 1, 2, 3, 4, 5, 6, and this little area here left blank. That would have been wrong. Okay, let's try one more. Let's try aluminum. So aluminum is over here. It's a metal, and its valence is 3 if you look at the top there. So you put the symbol for aluminum, and then you just go 1, 2, and 3. And that's how you do a Lewis dot structure. The amount of dots has to do with the number of valence electrons, which is obtained at the top of the periodic table. Okay, so let's go back to this example. So here we have sodium and chlorine getting together. And what you're looking at is what is called a Bohr diagram. Notice that in a Bohr diagram, the first energy level for sodium, because sodium has 11 protons, which means it has 11 electrons. So when you distribute the electrons, remember that you put 2 in the first energy level, so you see the first 2 right here. Then the next 8 go in the second energy level, so that's 10. And then the final one, which is in red, goes in the third energy level. So the first the first 10 electrons are called core electrons. They're not really involved in bonding. Only that valence electron at the end is involved. Now, chlorine is atom number 17. It has 17 protons, which means it has 17 electrons. So you'll notice there's 2 in the first energy levels, 8 in the second, and it has 7 valence electrons in the third. So what sodium wants to do is, for sodium, it's easier to lose 1 electron rather than to gain 7 to achieve the octet. Because it could gain 7, but why do that when you can just lose 1? So notice how the valence electron in sodium is being transferred to the chlorine. Now, as a result, if you look over here on the right side, sodium is no longer neutral. Sodium is now positively charged. It's a cation. Now, the electron gets transferred to chlorine. You see, chlorine has 7. Chlorine can either gain 1 to get the 8, or lose all 7. And for chlorine, it's way easier to just gain 1 than to lose all 7. So the electron that is lost from the sodium is given to the chlorine. Chlorine will accept it, as you can see on the right side of the picture, and chlorine will therefore become negative. As a result, here's what happens. When you put 2 ions that have opposite charges, there's going to be an attraction. This, what we call electrostatic attraction between this positive ion, which is the metal, and this negative ion, which is the nonmetal, is called an ionic bond. And what holds the bond together is the electrostatic attraction between the opposing charges, between the positive and the negative. And that's how they get together. Okay? Let's take a look at the next slide here. What we're going to do now is we're going to learn how to write the formula and name what is called a binary ionic compound. Now, when I say binary, that means that it consists only of 2 elements. Notice that the metal is always written first. The nonmetal is second. The metal will be the positive ion. The nonmetal will be the negative. When we name the compound, you will see that the metal, the name stays the same. However, the nonmetal, we're going to change it so it ends in IDE. It will adopt the suffix "ide." So sodium and chlorine would become sodium chloride. Magnesium and bromine would become magnesium bromide. Notice the "ide" gets adopted when the ionic bond forms. Calcium and oxygen will become calcium oxide. These are some common nonmetals that will adopt the IDE ending. As you can see on the left column, you have the element, and then here's the charge. It's going to, they're gaining electrons, so they're all going to become negative. And then here is the new name with the IDE ending. So, for instance, oxygen would become oxide. Sulfur would become sulfide. Iodine would become iodide. Nitrogen would become nitride. I know hydrogen isn't in here, but hydrogen would become hydride. The nonmetal will end in IDE. So let's do the following. We're going to use the periodic table to do a couple of examples. And then I'm going to introduce something called the crisscross method. Okay? So we saw that sodium was +1 and chlorine was -1. And there is a way to figure out the formula of an ionic compound by using what is called the crisscross method. And what we're going to do is the following. When you use the crisscross method, remember these are ones, even though you don't have to write them. The 1 over here crosses over and becomes the subscript of the metal. And then the 1 over here will become the subscript of the nonmetal. Now, if you recall, in chemistry, we don't have to write ones. Now, this is important. When you do this crisscrossing, you drop the signs. They're no longer positive or negative. You drop the signs, you ignore them. And since we don't have to write ones in chemistry, it becomes NaCl. And then when you name it, the first one is still sodium. The metal stays the same. And then chlorine will become chloride. And what this means is that sodium and chlorine got together in a 1-to-1 ratio. Now, I'm going to show you a Lewis dot structure of this. If you recall earlier, sodium has 1 dot and chlorine had 7 dots. It has 7 valence electrons. So what ends up happening is sodium will give the electron to chlorine. The sodium will now become just positively charged, and the chlorine will accept that electron. I'll use a different color here. And the chlorine will now be negatively charged, and that's how they interact. Let's take a look at another example, and we'll use the crisscross method again. Now, let's say I had aluminum getting together with chlorine. Well, the symbol for aluminum is Al, the symbol for chlorine is Cl. If we go to the periodic table, notice that aluminum has 3 valence electrons and chlorine has 7. So what I'm going to do here is I'm going to draw a Lewis dot structure. So aluminum has 3 valence and chlorine has 1, 2, 3, 4, 5, 6, 7, which we saw in the previous example. Now, what aluminum wants to do to be happy, if you recall, everyone in this group wants to lose 3. These guys want to gain 1. So, if you look at the periodic table and you go over here, aluminum wants to lose 3. Chlorine wants to gain 1. So what happens here, let's do the crisscross method. The 1 goes to the aluminum. The 3 goes to the chlorine. We don't have to write ones. This becomes AlCl3. Now, what this means is that for this to work out, for every 1 aluminum, you're going to need 3 chlorines. When you name this, the metal stays the same. It's still called aluminum. And then the nonmetal will be chloride. It will adopt the IDE ending. So you have aluminum chloride. Now, let me show you using Lewis dot structures how this works. So according to the formula AlCl3, we would have 1 aluminum and we would have to draw 3 chlorines. This is the ratio. Watch how this works out nicely. I'm drawing 3 chlorines, and if you recall, let me put they each have 7. Watch this. They each want 1 electron, the chlorines that is. But aluminum is going to give 1 to him. He's a happy camper. He's negative, he's got his octet, he's done. Aluminum lost 1. But aluminum is still trying to lose 2 more. So here's where a second chlorine comes in. Okay, let me put it over here. And he gives it to him. And now this chlorine is negative. He's a happy camper. But aluminum still wants to lose 1 more. And this is why you need a 3rd chlorine. The 3rd one, here's the aluminum, gives it to him. The chlorine is happy, but now finally, the aluminum was able to give 1 electron to each chlorine. He needed 3 chlorines to get rid of his 3. And finally, the aluminum is now happy and got his octet. Okay? Let's take a look at another example here. So let's say you had calcium and oxygen. So the symbol for calcium is Ca, oxygen's O. So let's take a look at the periodic table. Let me go back here for a minute. So calcium is over here. If you recall, these guys have 2 valence. They like to lose 2, so they're going to become +2. Oxygen has 6 valence. You'll see they like to gain 2. So let's take a look at this, at what happens. First, here's the Lewis dot structure for calcium. He has 2 valence, and oxygen has 6. And what happens here is calcium wants to lose 2. Oxygen wants to gain 2. Now, when you crisscross these two, look what happens over here. Whenever these two are the same numbers, here's what's going to happen. After you crisscross it, you are going to reduce this to lowest terms. So when you reduce, this becomes a 1-to-1 ratio, and you want to reduce it, and you want to write it in the lowest terms. This means that for every 1 calcium, you need 1 oxygen. Now, this makes perfect sense. If you look at let me fix this up here. If you look at my Lewis dot structure, okay, you'll notice over here that he's going to give 1 over here. He wants to give another one over here. You know what? I had drawn this incorrectly. I was trying to fix it. There were 6 here, and I apologize. Oxygen has 6 valence. So you put it there, okay? And here's what's happening. He loses his 2. He gains the 2 that he wanted. So the oxygen now has a -2 charge. The calcium has a +2 charge. And remember what I said earlier, opposites attract. And they get together. And when we name this, it's going to be called calcium oxide. Just like that. Okay? Let's do another example. So let's say we had potassium and nitrogen getting together. So potassium is K, nitrogen is N. Let's go to the periodic table and look at potassium. Potassium is an alkali metal. It likes to lose 1 electron. Nitrogen, in the nitrogen family, they have 5 valence. They want to gain 3. So let's take a look at how this all plays out. Let's go over here. So potassium has 1 valence. In fact, it wants to lose that 1. Nitrogen has 1, 2, 3, 4, 5 valence. And what nitrogen wants to do is gain 3. So let's use the crisscross method. So we know the 3 goes over here. Let's put a nitrogen there. The 1 goes over here. We don't need to write the 1, so it becomes K3N, which means that for every 3 potassiums, you need 1 nitrogen, okay? And when we name this, because that will be the formula, it's called potassium, and then nitrogen becomes nitride. Potassium nitride. Now, let's take a look at this. We'll go over here to this page here. We'll do K3N. So I need to draw 3 of these according to the formula. It's a 3-to-1 ratio. And then the nitrogen, I'm going to draw 1, 2, 3, 4. I'm going to put the 5th one over here to make it look a little nicer. So he's going to give 1 to him. And he's happy. He became plus 1. Nitrogen still is looking for 2 more electrons. So here comes the second potassium, gives 1 to him. Well, he's now happy. But the nitrogen still wants 1 more. This is why you need a 3rd. He's going to give it to him. He'll become positive. Finally, he got the 3 he wanted. And that's why when you use the crisscross method, you're always going to get the ratio of how many ions you need of each so that everybody is neutralized and stabilized. Okay, let's see if we can do one more. Let's try something like aluminum with, let's say, phosphorus. So aluminum, as we saw earlier, has 3 valence. Phosphorus is right beneath nitrogen. In fact, to save a little time, phosphorus has 5 valence. If you recall, aluminum, once it's in the boron family, aluminum wants to lose 3 electrons. phosphorus is just like nitrogen. It wants to gain 3. Okay, just like that. Now, I don't know if you see what I see, but we can anticipate something here. When we crisscross this, okay, the 3's will cross, but when you see that these are the same, they're going to cancel out. So this is going to become a 1-to-1 ratio, okay? And here you would just put ALN. You will not have to put the 3's. You do want to reduce it to lowest terms. And the formula, oh, I put nitrogen there. My mistake. I apologize. Let me fix that. I was going back to the last problem. Let's put the phosphorus there. I just noticed the mistake. So phosphorus and nitrogen, by the way, they would do the same exact thing. So you're going to have here aluminum, and then it would be phosphide. Remember, the nonmetal has to end in "ide." So even if it was aluminum with nitrogen, we would have still gotten a 1-to-1 ratio since they're in the same family. So here I corrected it. I put phosphorus, and we got aluminum phosphide. And you can see, and I'll demonstrate this, you got the aluminum here with the 3 valence, and you got the phosphorus here. Let's put the 5 valence. You can see it's going to be a perfect fit. He needs 3, and he's got 3 to give. So it works out perfectly. He becomes +3, he becomes -3, and all you need is 1 of each for the 2 of them to work out. Okay? Now, in a future video, I'm going to start adding the transition metals. We're going to start learning how they are affected. And we're going to also learn if you have elements that, let's say you have element X that has a +4 charge, and you have element Y that has a -2 charge, and I'm just being generic here. This can be reduced too. So when you crisscross and you get the 2 over here and the 4 over here, we will reduce this to a 1-to-2 ratio, and you would write it like that. We will be seeing that in the next video. I'm going to introduce the transition metals, which will be our next one, and also we're going to be looking at a video with polyatomic ions included. All of these would fall under ionic bonding. Okay?